Hello everyone. Welcome to today's webinar, Signal Analysis Made Easy. My name is Kirti Kumar Devlekar and I am the Technical Marketing Specialist for Signal Processing Toolbox. In the next 30 minutes, I will present a workflow which you can use to carry out signal analysis tasks. In the process, I will also showcase some analysis tools which you will find useful for performing signal analysis in MATLAB using a demo. So let us get started. Sensors are everywhere and generate signals in response to an event. It is for this reason signal processing is a major application area. You can find signals in the physical world and also in the electronic products that are so much part of our modern day life. Here are some examples you can relate to. For instance, an electronic keyboard synthesizes signals to generate sound waves. Wearable devices generate electric signals in response to human activity. Cars have sensors installed which can detect traffic passing by to prevent accidents, and electronic devices transmit and receive data using signals. Many scientists and engineers spend time understanding these signals and their characteristics to design products that do signal processing. So, why analyze signals using MATLAB? Well, the answer is simple. MATLAB makes signal analysis tasks easy. It is a high-level language and provides an interactive development environment to analyze signals and develop custom algorithms. The best part is you don't need a background in signal processing to analyze signals with MATLAB and Signal Processing Toolbox. Before we jump into the main demo, I would like to go over what we at MathWorks call the signal analysis workflow. This is the workflow you will use when you analyze signals. Basically, there are three steps in this workflow. In the first step, you need to gain access to these signals. You need to get these signals from somewhere into MATLAB. For example, these signals can be logged and stored in various formats, for instance, a file, a database, or can also be acquired using an hardware. Once you have your signals in MATLAB, the next step is to do what we call explore and discover. This is where MATLAB really shines. Often while performing signal analysis, there are times when you're unsure of what you're looking for, or you may be looking to find some patterns or trends in your signals. Using MATLAB, you can figure out the different ways and means to explore and analyze your signals to obtain insights. Using an iterative technique, you will discover what works for your signals and what doesn't, and subsequently develop applications or algorithms which suit your requirements. Once you're done developing an application or algorithm, you would want to share your work with your colleagues. There are different ways in which you can share your analysis. For example, you can choose to create a PDF or HTML report, or you may choose to use your analysis to feed a downstream process where you may be designing a device, a system, like a hardware. Or you may want to deploy the analysis to another environment by creating a C or a C++ or a Java component. In addition, MATLAB language provides powerful techniques to automate the mundane tasks, thereby making the entire process easier, faster, and also repeatable. In this webinar, we will focus mainly on the Explore and Discover section. With that introduction and background, let us come to the main topic of the webinar, which is a demo. In this demo, we will analyze seismic data generated by a seismometer during an earthquake to obtain some insights. We will analyze the signals and we will go over two demos. The first demo is to estimate the distance of the seismometer to the earthquake location. The second demo is to visualize the seismometer movement during the earthquake. Now, I'm not a seismologist and you don't have to be one to understand and follow along. I'm just using this example to showcase the different tools available for signal analysis. You can reuse these techniques to analyze other signals. Here is a simplified background of the seismic signal. A seismometer is a device which is sensitive to vibrations occurring due to the earthquake and captures the magnitude of these vibrations along three dimensions, that is, vertical direction, north-south direction, and east-west direction. There are two types of shock waves that occur before the main earthquake occurs. Those are P waves and S waves. P waves are the first waves to reach the recording station, followed by the S waves, which are then followed by the main vibrations that occur due to the earthquake. P waves are the fastest waves to reach the recording station and manifest as a small peak on the seismogram. These waves travel nearly vertically upward from the source of the fault and are the fastest waves. S waves, on the other hand, travel a little slower than the P waves, and these waves also manifest as a small peak. In our case, the seismometer was located in the vicinity of the earthquake, and hence the P waves will be more prominent on the vertical component, and the S waves will be more prominent on the east-west and the north-south components. The goal here is to identify these signals and measure their arrival times. A difference in the arrival times will provide an estimate of the distance of the seismometer from the earthquake location. Note that this is a simplistic approach of estimating the distance of the earthquake from the seismometer. In practice, geologists use sophisticated techniques to determine the distance. There are also other waves, excluding the ones I mentioned above, that are generated by the earthquake, but for the purposes of our webinar, we will not be going into the details of those waves. Let us switch to MATLAB. Let us first load the signals generated by the seismometer. These signals have been stored in a DAT file. You can easily import these signals by using the Import Tool functionality. To do this, go to the Home tab, click on Import Data. Select the file which contains the readings of the signals and hit Open. In the following screen, you can choose from various options depending on how your data is actually stored in the file, specify how you would like to import your data into MATLAB, and hit the green button which says Import Selection. The signals are now imported and we now have 4 column vectors. 3 of the 4 column vectors contain acceleration signals experienced by the seismometer, and the 4th column vector contains the time information. You can automate this process by clicking on Generate Script, and this creates a MATLAB script with the options you have chosen while importing the data. I have already saved my script with the name Import Quake Data. The sampling frequency of these signals is 200 Hz. Now that we have got our signals in MATLAB, the first step is to visualize the signals in time domain. You can use the plot command to visualize the signals in time domain. I'm using a helper function I created to visualize all the signals captured along the 3 dimensions. Let me execute the helper function. Executing the script, I see there are 3 plots here. The plots show the acceleration signals in vertical direction, north-south direction, and east-west direction. I would like to remind you all that to estimate the distance between the seismometer and the earthquake, we need to identify P and S waves and their arrival times, as discussed earlier. In our case, the P waves are prominent on the vertical component. But before I jump in to detect my P waves, how can I make sure that this signal does not contain any artifacts or unnecessary components? The P waves will show up as peak on the vertical component, but how can I distinguish a peak caused due to a P wave from a peak that is caused due to noise? It is even harder to tell this just by looking at the time domain representation of the signal. So the challenge here is, how can I determine if I need to pre-process my signal? Now, usually when you analyze signals, you would know something about the signal beforehand. In this case, one property I know about the P wave is that these signals have a maximum frequency of 25 Hz. Another thing I know is that the signals generated from earthquake have frequency components changing over time. So it makes sense to visualize this signal in time frequency domain. To analyze the signal in time frequency domain, you can use the function spectrogram. This function is available in the signal processing toolbox. I pass in the signal, the sampling frequency, as input parameters to spectrogram and use the empty square braces for other input parameters. Note that when you specify empty square braces for an input parameter, default values are assumed by spectrogram. Executing the spectrogram function without the output arguments displays the signal in time frequency domain. I would like to mention here that most of the functions in signal processing toolbox automatically generate plots when no output arguments are provided. We can see here how the frequency of the vertical component varies as a function of time. The power of the signal is also available in form of color. The blue color depicts low power levels and yellow color depicts high power levels. You can view the documentation of spectrogram for a detailed list of parameters you can provide as input and to learn more about the default values for the input parameter. Let us take a closer look at the spectrogram. There is something interesting here. If you notice closely, the upper half of the spectrogram, that is beyond 40 Hz, the color pattern is pretty much same along the entire duration of the signal. The color intensity of these signals suggests that the power levels are high. The presence of these components does not add any value to the analysis of this signal. Now looking at the lower half of the spectrogram, based on the color profile, I see that there are three distinct bands. Band 1 extends from 0 to 13 seconds approximately, and it is here where P and S waves are most likely present. Notice the yellow and orange colors. Band 2 extends from approximately 13 seconds up until 25 seconds. This most likely corresponds to the time instant at which the main vibrations from the earthquake occurred. Notice the light yellow color, which indicates a high signal power level. Band 3 extends from 25 seconds up until the duration of the signal. Notice that the color profile changes from light blue at the beginning of the band to the dark blue color at the end of the band. Now the color bands in the lower half of the spectrogram seem to transition into upper half of the spectrogram somewhere after 22 Hz and before 40 Hz for the entire duration of the signal. Based on this analysis, I can choose a cutoff frequency for my low pass filter to be anywhere from 22 Hz to 40 Hz. I also know that the maximum frequency of oscillation of my P wave is 25 Hz. So we will design a low pass filter with a cutoff frequency of 25 Hz to eliminate the high frequency signals. From this analysis, I can conclude that there is a need to pre-process my signal. Thanks to the spectrogram function in Signal Processing Toolbox, which has really helped me in figuring out that a pre-processing step is essential. Now that we have determined that we need to get rid of frequency components more than 25 Hz, we can design a low-pass filter. Now, filtering is a two-step process. In the first step, we need to design the filter, and in the second step, we need to apply the filter to our signal. To design a filter, you can use the function designFilt. In our case, we need to get rid of the high frequency components, so I'm choosing to design a low pass IIR filter. I specify low pass IIR as an input parameter to the designFilt function and execute the function from the command prompt. This launches a filter design assistant which helps me with the process of designing a filter. I specify the sampling frequency as 200 Hz, passband frequency as 20 Hz, and stop band frequency of 25 Hz. Clicking on OK generates the code in command prompt which can be used to design the filter. Note that with Design Filt, you can design a variety of filter responses and types. For more information, please look up the documentation of the Design Filt function. We can now apply the filter we just designed on our signal using the function filter. The function takes in low-pass filter we just created as input and the signals. We filter all the three signals. The filter function effectively removes the high frequency component for all the three signals, and what we now have is a pre-processed version of the original acceleration signal. Now, although the filtering process in the previous step has removed the high frequency components, it also introduces a delay in the filtered signal. In other words, the samples of the filtered signal are delayed with respect to the original signal. In this case, we are using a low-pass IIR filter, and the delay introduced by a low-pass IIR filter varies as a function of frequency. If we do not compensate for the delay introduced by filtering, the arrival times for the P waves and the S waves after we detect them will be incorrectly measured, and this may lead to erroneous distance estimate. To visualize the nature of the delay caused by our filter, we can use the function group delay. We specify the filter we just designed, a number greater than the order of the filter, in this case 500, and a sampling frequency as input to the group delay function. Now, if you want to find out the order of the filter you just designed, it is easy. You can use the function filter order and pass in the filter we just designed as input, and this returns the order of the filter. Executing the group delay function plots the delay introduced as a function of frequency. You can clearly see that as the frequency of the input signal changes from 10 to 20 Hz, the corresponding delay introduced increases non-linearly as depicted on the y-axis. In other words, as the frequency changes from 10 Hz to 20 Hz, the delay varies from 35 samples to 85 samples approximately. To overcome the delay introduced by filtering and have the filtered signal track the original signal more closely, you can use the function filtFilt instead of the function filter. FiltFilt performs zero phase filtering. In other words, it compensates for the delay introduced while filtering and aligns the filtered signal with the original signal. Let us use the function filtFilt to filter our signals. The filtFilt function takes in as input the low pass filter we just designed and the original signal. The output is a delay compensated filtered version of the original signal. I'm using a helper function to compare the output of filtFilt, the output of filter, with the original signal in time domain. Let me execute this helper function. Executing the helper function, we see there are three signals here. We have the original signal in blue, the filtered version of the original signal in black, that is the output of the command filter, and the filtered and delay compensated signal, that is the output of filtFilt, denoted by the red color. You can clearly see how the output of filtFilt smooths the original signal and also tracks it closely. Now that we have pre-processed our signal and removed the delay introduced while pre-processing, let us now try to detect a P wave and find its arrival time. Recall that P waves travel almost vertically and are the first waves to be recorded by the seismograph, and in our case are found on the vertical component. So the goal here is to find a peak on the vertical component and obtain the time instant at which the peak occurs. We can do so by using the function findPeaks. I would like to mention here that in practice, geologists use sophisticated techniques to detect P waves and S waves and their arrival times. But going over those techniques is out of scope of this webinar. The main idea here is to show you how you can go about locating peaks in your signal. Let us now see how we can go about locating peaks in our signal using the findPeaks function. You can pass in the signal and the sampling frequency as input to the findPeaks function, and it displays all the peaks in the signal automatically. We see that using findPeaks with default inputs provides us with a lot of peaks. Some are small and some are large. As I mentioned earlier, P-wave manifests as a small peak on the vertical component. So for our purposes, I would like to locate the P-wave by looking for a peak whose amplitude is at least 10% of the maximum value of the vertical component. In reality, choosing the right value for the amplitude depends on a lot of factors and is actually a matter of judgment and subject level expertise in geology. For our purposes, we are selecting the value to be 10% of the maximum value of the vertical component. We now add a min peak height parameter to the findPeaks function and set the value accordingly. Executing the function returns all the peaks that satisfy our criteria. Those were still a lot of peaks. Since we are only interested in the first occurrence, we can limit the number of peaks to 1 by adding another parameter npeaks and setting the value of this parameter to be 1. Now executing this function successfully locates a peak which corresponds to the P-wave. Now as a side note, I would like to mention that by specifying a couple of output parameters, the function returns the peak amplitude and their locations in time which satisfy our criteria. The variable Tp now contains the arrival time of the P-wave. This way we obtain the time instant at which the first P-wave has occurred. Now that we have the location of P-wave, let us focus on determining the time instant at which S-wave occurs. The S-wave can be found on east-west component and north-south component. We will use a similar criteria to locate the S-waves as we used for the P-waves. I will look for a peak whose amplitude is at least 10% of the maximum value of the respective components and store the peak location and amplitude in variables T22 and pk2 for the north-south component and in T33 and pk3 for the east-west component. I execute the script now and it looks like the S-wave is detected on the east-west component first, and after a few seconds the S-wave occurs on the north-south component. We choose the arrival time of the S-wave as measured on the east-west component as it occurs first. I can also visualize S-waves and their location as detected on the north-south and east-west components with the help of an helper function. Now, if the criteria for locating the peaks changes for some reason, we can always go back and plug in new numbers for the amplitude values, or look for a peak using other parameters. For a detailed list of available parameters, please look up the documentation for findPeaks. Now that we have detected the P waves and S waves and their arrival times, a quick way to find the distance between the recording station and the earthquake can be done by determining the time difference of the arrival times of these two waves and multiplying the difference with the velocity of these waves. Now the velocity of these waves varies on a lot of factors, for example, the geological composition of Earth, the density of the layers, etc., and other factors. For simplicity, we will use the average value of 8 kilometers per second for the velocity. Multiplying the difference in the arrival times with the average velocity, we can estimate the distance of the earthquake from the seismometer to be around 22.36 kilometers. Plotting a circle with the location of the seismometer as center and the radius of 22.36 kilometers on a map gives all the possible locations of the earthquake. In this way, we can estimate the distance of the seismometer from the location of the earthquake. We have seen how MATLAB and Signal Processing Toolbox makes it easy to analyze signals and estimate the distance of the seismometer from the earthquake. This concludes the first demo. Let us now move to the next demo. In this demo, I would like to go over how you can obtain displacement information from acceleration data we already have to visualize the movement of the seismometer during the earthquake. Let me open the MATLAB script for this demo. So the goal here is to obtain displacement from acceleration data. We can integrate the acceleration data we have and multiply it with time differential or the inverse of sampling frequency to obtain velocity, and we can repeat the same step on the velocity to obtain the displacement. Now, an integrator is basically a filter with transfer function 1 over 1 minus z inverse. The coefficients of this filter are specified by the variables nr and dr. Using these coefficients and the input signal, that is, the pre-processed acceleration signal from the previous demo, I can use the filter command to obtain the velocity in the vertical, north-south, and the east-west directions, and repeat the same step to obtain the displacement. Let us now view the range of the displacement numbers we've just computed. The displacement numbers seem to be 221 centimeters, 574 centimeters, and 356 centimeters. The negative sign indicates displacement in the opposite direction of reference. Now, one does not need to be a seismologist to realize that something is wrong here with the displacement numbers we have just computed. For instance, 575 centimeters is equivalent to the device moving about 19 feet, which is roughly the size of a two-storied building. That number does not sound reasonable for a seismometer displacement. At the same time, we have not done anything wrong either. Double integrating acceleration to obtain displacement is a standard technique, and we exactly did that. So, what could have gone wrong here? Let us investigate and find out what is going on here. To troubleshoot, as a first step, let us compare the acceleration and the velocity data of the east-west component. Give me a moment here. Now, looking at these plots closely, I see something going on here. It seems like sometime after the earthquake dies down, that is, after 30 seconds on the acceleration plot, the seismometer looks like it is returning to steady state. But during the same time, the velocity plot seems to have a drift associated. It keeps on increasing. Let me go back and see if this is the case with the velocity computed for the north-south direction and the vertical direction. I will use a helper function to compare the velocity along the three dimensions. Now, looking at these plots, it is clear that there seems to be some kind of drift associated with our measurements. Clearly, this drift is most likely the cause of erroneous position values calculated earlier. We need to account for this drift to obtain reasonable displacement numbers. Now, to remove the drift associated with these measurements, I can use the dtrend function. This function is capable of removing linear trends associated with our signal and returns a drift-free signal. I pass in the pre-processed acceleration signal as an input to the dtrend function, and I will compute the velocity from the detrended acceleration signal. Let us compare the velocity before and after detrending. Now, looking at these plots, I see that velocity, denoted in blue, seems to obtain a steady state after detrending the acceleration signal. From this, I can conclude that the detrend function was successful in removing the drift. Let us now proceed to compute the displacement values and take a look at the results. The displacement numbers certainly look reasonable. We can now visualize these displacement numbers using a 3D plot. You can use the function plot3 to visualize the position of the seismometer on a 3D plot based on the displacement numbers we just computed. In this way, we can visualize the displacement of the seismometer by computing displacement from acceleration. This information could be used by, for instance, a structural or civil engineer to understand how a structure moves during an earthquake and help them design better quake-resistant structures. This concludes the demos in the webinar, but we are not done yet. Now that we have completed the analysis, it is time for us to share our analysis with others. For instance, you may choose to create a report of your analysis in an HTML form. To do that, you can use the command publish and pass in the name of the script as an input parameter. This creates a HTML version of your script and you can share the HTML file with others. Let us return to the PowerPoint presentation here. You also have other options to share, like for example, you can create an app based on the analysis you just carried out and choose to create a standalone application or Excel add-in using the MATLAB compiler to share your analysis with others who do not have access to MATLAB. You can also choose to create C or C++ component or a Java component and integrate your analysis in another environment like a web application using the MATLAB compiler SDK. To wrap up, MATLAB and Signal Processing Toolbox makes signal analysis very easy. We have seen how easy it is to import signals in MATLAB, analyze and explore signals, and share your analysis with others. Here are a few functions we have used in the process of analyzing our signals in our demo, which are available in the Signal Processing Toolbox. There are also a few additional features and capabilities in Signal Processing Toolbox, including signal generation, signal measurement, and techniques to analyze non-uniformly sampled signals as well. This brings us to the end of the webinar. Thank you for joining.